Today we're going to talk about partial fraction decomposition. This is still in section 7.3. It's a systems of equations application. So we're going to have multiple unknowns with multiple equations. We can solve that using substitution, elimination. Technically we could solve it using graphing, or we can use matrices. To set up what a partial fraction decomposition is, I'm first going to do a problem over here on the right where we simplify 4 divided by x minus 3 minus 1 divided by x plus 2. Simplifying this would include creating a common denominator. I need to multiply both terms by x plus 2 over x plus 2, and then the second by x minus 3 over x minus 3. This will give me a common denominator. Distribute the 4, distribute the negative 1. I'll get a numerator over this common denominator. In the numerator, I'll get 3x plus 11. In the denominator, if I were to FOIL that out, I would get x squared minus x minus 6, which we already see over here. We've done this type of problem for a long time. But the question now is, could we go the other way? Could we start with the 3x plus 11 divided by x squared minus x minus 6 and split up that fraction into two different terms? Could we decompose, could we separate these fractions? There is a proof, and I'm not going to go through the proof, but the proof says that 3x plus 11 divided by the quantity x minus 3, x plus 2 must be equivalent to some number over x minus 3 plus some other number over the factor of x plus 2. That must occur. We are so used to going from the separate fractions to a single denominator. Now we're going to work on decomposing these. We're going to start with this example. We already know the answer to this. We're just going to work backwards. The theory is that 3x plus 11 divided by x minus 3, x plus 2 must be equivalent to a over x minus 3 plus b over x plus 2. The way we're going to solve for a and b is very similar to what we already started with. We're going to multiply by x minus 3 over x minus 3, x plus 2 over x plus 2, and I will get that 3x plus 11 must be equivalent to a times x plus 2 plus b times x minus 3. The denominators are all the same, so we're going to ignore those at this point. From here, I'm going to solve this equation two ways. One is going to be using a systems of equations as we typically know it. In the first method, I'm going to distribute the a and the b, so I get 3x plus 11 equals ax plus bx plus 2a minus 3b. I've distributed and reorganized. What I can show is that this 3x must be equivalent to the a plus bx because those are the only terms that involve x. So 3x must equal ax plus bx, so 3 must equal a plus b. That's one equation. The second equation will come from the fact that the 11 has to equal the constants, so 11 must equal 2a minus 3b. I now have two equations with two unknowns. I'll rewrite these so that they're in nice standard form. A plus b equals 3. 2a minus 3b equals 11. I can solve this using a matrix. I can solve this using elimination. I can solve this using substitution. I get two values. I get an a value of 4. I get a b value of negative 1. And then I could rewrite my initial problem by plugging in a. So I get 4 over x minus 3 minus 1 over x plus 2, which is equivalent to the 3x plus 11 over the x minus 3, x plus 2. The second technique that I'm really going to push is not quite the same as our traditional system of equation. I've got this x plus 2 times a, and I've got this x minus 3 times b. What I can do here is I can use certain x values. I'm going to use an x value of negative 2. And the reason I'm going to do that is because it makes this quantity equal to 0. When I plug in negative 2, I'll get 3 times negative 2 plus 11 equals a times 0 plus b times negative 5. On the left side, I'll get 5 equals 0 times negative 5b, I'll get a b value of negative 1. The second value I'm going to use is I'm going to use an x value of positive 3, and the reason is because it will make this quantity of x minus 3 equal to 0. I'll plug in 3. I'll get 3 times 3 plus 11 equals a times 3 plus 2 plus b times 0. On the left side, I will get 20 equals 5a, and a will come out to be a value of 4. I can rewrite my final answer to say 4 over x minus 3 minus 1 over x plus 2. That is equivalent to my 3x plus 11 over the x minus 3 times x plus 2. I'm going to strongly suggest using option 2. Two other examples we're going to do here before I leave you with some practice. 2x minus 5 divided by the quantity of x minus 4 and x plus 1 must be equivalent to some value a over x minus 4 plus some value b over x plus 1. We're going to search for that a and b. We're going to start by multiplying to create a common denominator, and then rewrite the numerators to be 2x minus 5 equals a times x plus 1 plus b times x minus 4. The denominators are the same, so we can ignore those. I'm going to insert two x values. I'm going to use first an x value of negative 1 because it makes my first quantity equal to 0. When I plug in negative 1, I get 2 times negative 1 minus 5 equals a times 0 plus b times negative 5. On the left side, I'll get a value of negative 7 equals negative 5b. b equals 7/5. I'm then going to use an x value of 4. I will get 8 minus 5 equals a times 5 plus b times 0. Here I'll get an a value of 3/5. These don't work out cleanly as integers, but it still is true. We can plug back in our a and our b, and we would say that our final answer here would be 3/5 divided by x minus 4 plus 7/5 divided by x plus 1. We could rewrite that so it's not a complex fraction, but we're going to leave it there for now. The final problem we're going to do here conveniently comes with a factored denominator. However, we see three factors. We have an x minus 1, an x plus 2, and an x plus 2. Something I briefed over earlier was that we need a over x minus 1 plus b over x plus 2, but we also are going to need a third term here of x plus 2, that quantity squared. I'm not going to get into the proof here, but you certainly can if you want to dive further into that. Here we could rewrite the numerators to be 6x squared plus 21x plus 9 would equal a times the x plus 2 squared plus b times an x minus 1 and another x plus 2 plus c times an x minus 1. Here I have three unknowns, so I'm going to need to plug in three distinct values. I'm going to start by using an x value of negative 2. When I insert negative 2, I'll get 24 minus 42 plus 9 equals a times 0, b times 0, and c times negative 3. This will yield negative 9 equals negative 3 times c. I'll get a c value of 3. I'm then going to use an x value of positive 1. This will yield 6 plus 21 plus 9 equals a times 3 squared plus b times 0 plus c times 0. I'll get 36 equals 9a. I'll get an a value of 4. So how do I finish this off? I'm just going to pick a third value to plug in. I'm going to use an x value of 0 because I think 0 is easy to plug in. When I plug that back in, I get 9 on the left. I get a times 2 squared plus b times negative 1 times 2 plus c times negative 1. I already know my a and c values, so I can get 9 equals an a value of 4 times 4 plus b times negative 2 plus my c value is 3 times negative 1. I can solve that to get a b value of 2. I can rewrite my final answer now. Going back to the initial problem, I can replace a with 4, b with 2, and c with 3. After erasing out those values, I can put in a 4, 2, and 3 to find my partial fraction decomposition. I'm going to leave you with 2 questions. Decompose these 2 fractions, 7x plus 13 over a quadratic and 2x squared minus x plus 3 over a cubic. Think about what's going to be necessary for that cubic. Good luck.